Hello, everyone. Good morning, good afternoon, depending on where you are. For me, it's actually good evening. And welcome to this Ophir Photonics webinar. My name is Mark Slutsky, Product Manager for Power and Energy Measurement Solutions here at Ophir Photonics. And thanks for joining us today. We're going to be talking about a topic of some passing interest to those involved in precision measurements. I'm being a little bit facetious. We're going to be talking about calibration and accuracy of laser measurements, power measurements, energy measurements. It might seem a little bit of a philosophical-ish almost topic, but I somehow think that anybody joining a webinar on a topic of this nature goes beyond that and understands the importance of it. By way of introduction, I might even just add a little comment that companies such as Ophir, we design and manufacture and offer measurement instruments for lasers, users of lasers, integrators, producers of lasers, whatever. The actual product that we offer, if you think about it, is accuracy of the end user's measurements. The stuff that you see in the catalog and in the website, all of those things are vehicles to deliver the product. So this is really what we're all about. Just on a logistical note before we jump in, the total time of our discussion today should be approximately 45 minutes or so. Questions, comments are welcome. If you have any questions or comments, please use the text chat box on the right side of your screen, and I'll do my best to respond either in real time or at a suitable point in the flow of the information, depending on the nature and the timing of the questions or comments. I should just add that the GoToWebinar platform that we're using now, we just started using in the last week. It's kind of new for us. So if there are little technical glitches that I bump into, then I apologize in advance. Hopefully it won't come down to that. For example, this morning I gave this webinar for the other side of the planet, and only near the end I realized that the chat box was not visible because I had minimized it. So just little things like that. Okay, so let's, oh, and just one other, I guess, logistical note. I'll be leaving my contact information up on the final slide for a minute or so after we're done. So in case rather than, or in addition to asking a question or offering a comment here in the chat, if you want to get in touch with me offline, you're more than welcome to do that. I'll leave my email address up on the final slide. Also on the bottom of every page on our website, there's a contact us form. I think we call it contact us, request support. I don't remember what it says there, but we want to make it as easy as possible for you to get a hold of us if there's any way at all in which we can serve you. And just one additional point is I've done everything I could to keep the information as generic as possible so that it'll be as helpful as possible to as many of you as possible. Our goal here isn't to, give a plug for some particular product or other. Nevertheless, if it, when it comes down to actual examples of either instruments or in this discussion, more like processes and concepts, then the actual examples, as you can appreciate, are going to be referring to Ophir examples because obviously those are the ones that I can talk about. Okay, so let's begin. So I'm not going to dwell on this. I assume you're at least somewhat familiar with Ophir. You might already be using Ophir instrumentation or instrumentation like Ophir, God forbid, from some other manufacturer. But I'm assuming that you're somewhat familiar with the basic concepts. Basically, what I said on this slide, if I can really summarize it down, is that we like to do the hard stuff that you would really be happy to get off your head so you can focus on the work that you're doing and not worry about the tools that you need to do to help you get the work done. Some years back, Ophir was acquired by Newport, and then some years after that, Newport, along with us, became part of MKS Instruments. I think that's a fair summary of what it said on that slide. So here's what we're going to talk about. First, just so that we're speaking the same language, we're going to define our terms. That always is very helpful. And I want to just talk a little bit, very high altitude, about the meaning and importance of accurate calibration, when, how, why, and to be perfectly honest, when it might not really be all that critical. It might be surprising to hear that from someone who works in a company like Ophir, but it is part of reality. I'm going to briefly give you a few tastes of where the numbers that we give in our data sheets regarding accuracy, where those numbers come from. So if at the, in the specification of a particular laser power sensor, if it says that the measurement accuracy is plus minus 3%, now where did that number come from? So I'm gonna, obviously it's way too big a topic to cover in detail. That's not exactly our purpose. I wanna just give you a taste of the sort of places where that number comes from. I'm gonna show you just one or two examples. More importantly, I'm gonna point you in the direction of much more detailed information, which we have available and I'm more than happy to share. So for those of you who do want to get a deeper understanding of it, you'll know where to find that information. We want to share that with anybody who wants it. Then we'll get into the more practical stuff, things that a manufacturer of precision laser measurement instrumentation like Ophir does so that the instruments that you get can deliver the best accuracy possible. And probably more interesting, we're going to give you a few black belt best practices that you can adopt so that you'll get the best possible accuracy performance out of whatever instrumentation you're using. And then for the last few minutes, I want to give a breakdown of the Ophir certificate of calibration, what's in it. Those of us like me who aren't QA professionals, sometimes it looks like some foreign language or whatever. There is a very logical structure to it. It speaks in the formal language of the quality standards, the ISO standards that we're certified to. So I just want to show you what's in there so that it'll have some meaning. After all, that document tells you how accurate the instrument you're using is, and it might be of some relevance to know how to read that. So let's begin with the beginning. First, let's define our terms. When we talk about accuracy in the data sheets, that might show up as absolute accuracy or measurement accuracy. What we mean is when you use this instrument to measure, let's say, the power in a laser beam, how close is that measurement to the absolute truth? Now, you notice I put absolute truth in quotation marks. I, for one, don't usually have such clear access to the absolute truth. I would tend to be nervous being around somebody who thinks that they do. So what we mean by absolute truth in this context is what NIST or an equivalent international standard body, German PTB, for example, would say that the measurement result should be. So if a given laser power meter, measures the power as so-and-so, how close is that to what NIST would say the power really is, plus the uncertainty in NIST's own measurements. They're also not perfect. They publish this data. What we call in the data sheets measurement uncertainty, that is the range of reading values above and below the calibration measurement value within which we expect. Now, here's a bit of a funny bit, 95% of cases in the case of Ophir to actually fall. In other words, it's a confidence level when we say that the accuracy of this instrument is, let's say, plus minus 3%. Why am I talking about confidence level? Because as we're gonna see over the next few minutes, everything here really revolves around statistics. In Ophir data sheets, we always base everything on a 2 sigma standard deviation. If you don't know what on earth I just said, don't worry about it. But those of you who do know what I said will appreciate the meaning. Basically, everything is really a question of probability. If I tell you that, oh, how accurate is this laser power meter? It reads precisely 1.379% high. I've just presented a perfectly accurate meter. There's no such thing. Because as soon as I tell you exactly how far off it is of the absolute truth, we're pretending that I knew what the absolute truth was, and I don't. I only know probabilities. Keep in mind that there's a difference between measurement uncertainty, which is the bottom line uncertainty that's specified in the data sheet of a measurement instrument, so that when you use it and you get a reading, that's the uncertainty level in your measurement, as opposed to calibration uncertainty, which is the uncertainty in our internal calibration process. That's something that's invisible to you, not the value. We publish the value, but the calibration process is something that happens in our calibration labs. It happens before the instrument got shipped out the door. What interests you is the bottom line uncertainty that you can expect when you're using it. We provide in our data sheets both numbers, but these are two different numbers. And we'll bump into that again in a couple of minutes. So just for example, let's say you use a laser power measurement, a power meter from Ophir, and you're measuring 1.00 watts. And the data sheet of that particular instrument tells you that its accuracy, the measurement accuracy is plus minus 3%. That's a pretty typical value. So that means that the true power of that beam is going to be somewhere between 3% above or below 1 watt. And even that statement, we're saying with a 95% confidence level in the case of Ophir. We need to differentiate between two similar but not identical terms, accuracy and precision. Precision is sometimes also referred to as repeatability. The accuracy is what we just described. It's a measure of how close a given reading is to the absolute truth. Typical accuracy specification for our power sensors, let's say, might be plus minus 3%. For the very high power water-cooled sensors for multi-tens of kilowatt industrial beams, it might be a little higher, plus minus 5%, because there's a lot of additional noise from the water cooling and the mass of the sensor and so on. And then in the data sheets, by the way, there will also be a few additional things, additional error with frequency if it's a energy per pulse sensor, linearity with power, additional error with wavelength, all sorts of additional things. So wait a second, you might ask, does that mean that the actual bottom line uncertainty in my measurement is not plus minus 3%, but it'll be plus minus 3 plus 1 plus 2 plus 1%? So the answer is, it depends. We're not going to get into the depths of it, but I just want to give you the bottom line, I guess we'll call it. When the various sources of uncertainty are random, like noise, the calibration accuracy, additional uncertainty with wavelength or whatever. If it's a source of uncertainty that's random, like noise, or like tolerance, surface uniformity tolerance across the aperture of a sensor, it's a random variation. So random sources of error get added not linearly, because while this source of error might, in this sensor's case, be giving it an incorrectly high reading, that other source of uncertainty might, in this case, happen to be giving it an incorrectly low reading. So they're not adding linearly, they're adding statistically. It's actually the root of the sum of the squares. On the other hand, if it's not a random error, then it would be added linearly. There's lots of detailed discussion of that on our website. I just wanted to get that concept out on the table. I should just mention that we, for quite a few years, have been certified under ISO 17025, which is an international standard that defines, let's call it the quality of work of a calibration lab. And so a lot of the terminology that we're going to use here is defined by the ISO standards, and we kind of have to play along with their rules. So sometimes some of these things might seem like we're hair splitting or whatever, but there is a method to the madness here. All right, so that's accuracy. It's a measure of how far a given reading is from the so-called absolute truth. Precision, on the other hand, is something completely different. It's the degree to which repeated measurements of a quote-unquote perfectly stable laser will keep on giving the same results. So I might have very tight precision. The noise in the sensor is very low, my conditions are stable, so the sensor keeps on measuring, giving me exactly the same measurement. That measurement, which means the precision is high. The measurement accuracy might be completely off. I might be 10% low, but I keep on getting the same reading every time, so I've got good precision but bad accuracy. Or I might have good accuracy but a lot of variability from measurement to measurement. So, okay, you get the idea. The precision or repeatability in the very best case is going to be limited by the noise of the measurement instrument, obviously. Typically, it's not only the noise, it's typically going to be a little bit worse than the noise. Typical power measurement precision or repeatability some will be up to plus or minus 1%. It's usually quite a bit better than that. For thermal type power sensors, it'll depend on the thermal stability of the environment. If you're in an air-conditioned lab and there's an air conditioner blowing directly on your thermal power sensor, you're going to get more variation. If the thermal environment is nice and sterile and stable, then you'll get much better repeatability and you'll get pretty close to that noise level, which is the absolute minimum. Calibration is the process of comparing a measurement from the instrument being calibrated to a known reference, let's say a NIST-provided reference sensor, to determine if it's performing within spec. It would probably be more correct if I said to determine how close, well, if it's performing within spec, how far it is from the reference, from the absolute truth. It can include an additional step of then adjusting the instrument being calibrated so that it actually reads as close as possible to that reference. But strictly speaking, it doesn't have to include that adjustment. Using the definitions of the ISO standards, it doesn't actually include the adjustments. If I give you a measurement instrument and I tell you that this instrument reads to within plus or minus 3% of NIST, then that's fine. Then you measure it, or even if I, you know what, even if I tell you that it reads 10% below NIST with a, to within plus or minus 3%, that's also fine, because then you know that you take off, you add 10% to what, and then you have a reading that's within plus or minus 3% of NIST. So even if I didn't actually make that adjustment, if I told you exactly what the deviation between this instrument that I'm giving you and NIST, if I tell you exactly what the deviation is, that's good enough. In practice, a commercial supplier of measurement equipment like Ophir will generally, yes, do that adjustment step. Again, sorry for the hair splitting, but there are quite possibly some QA professionals among you, and I have to be accurate and precise in what I'm saying. Obviously, there has to be traceability to an accepted standard. Mostly in our industry, we refer to the American NIST as the standard, but it could just as easily be the German PTB or any other equivalent international, equivalent national standard body, as long as we both know what we're talking about. And there is a time limit, because at least in Ophir's case, the instruments that we make happen to be made of matter, and matter drifts over time and over use, but also over time. Even if there's no use, we're going to come back to that. When is accuracy important? So let me give you a counter example. If you're a manufacturer of, let's say, handheld laser pointers for office presentations, 0.5 milliwatt, whatever it is, if it's 0.6 milliwatt, if it's 0.35 milliwatt, honestly, it probably doesn't matter. Presumably the engineers who designed it had a laser power meter to make sure that their design is right. Beyond that, since you're not really at much risk of the power being above some maximum set by the eye safety standards, in an application like that, it very possibly is not so important to perform measurements. I don't think any laser pointers used for office presentations have built-in monitoring capability, as opposed to a surgical system based on a laser will, yes, have a built-in measurement capability. You get the idea. So all lasers and delivery systems, at least the ones made of matter, degrade with time and use. and so do measurement instruments, obviously. So if your process, for example, here we see, I hope you can see my cursor, a laser for dental applications. Here's a laser head in an industrial laser cutting application. In these sort of cases, the process depends very much on exactly how much power and energy and a few other parameters, the exact parameters of the beam that's arriving at the target surface. And so to the extent that the process matters, the actual details of what's coming out of the laser also matter, and it's important to monitor them. How often to monitor them, how, where, that already depends on the details of the application. We've got lots of white papers and videos and pre-recorded webinars on our website about those, but the basic idea is important to be clear on. Now, even if you're clever and you're experienced and you're familiar with the importance of monitoring the performance of your laser, because it's important that your process stay stable and predictable and profitable. You want to keep scrap to a minimum and so on. So you've built in an internal monitor which takes some small percentage of the laser's output and keeps track of that. That's great. In some applications, that's perfectly sufficient, but in some applications it might not be. For example, there might be other issues that come up farther downstream. There might be some misalignment in some component in the delivery optics, or process debris might have contaminated the final focusing lens, so some of that light's getting scattered and is not reaching the focal point in the target plane, and so on. Here you see a serial number that's been laser marked on a jet engine blade. Some time back, we were helping a customer who manufactures jet engine blades, and they have an industry requirement, not a regulatory requirement, an industry requirement that every blade have a serial number, so that in case, God forbid, of accident investigation that concludes that a particular accident happened because of a faulty jet engine blade or a turbine blade or whatever, they can track down every other blade that was produced during that same shift on that same machine by that same operator anywhere else it is in the world, and perform preventive maintenance. So a lot of industries are self-regulating, even if they're not government regulated, like the medical industry is, for example. Semiconductor industry is certainly self-regulating because mistakes in the process there, here you see, for example, via holes in a silicon wafer, can end up costing quite a bit of money. Medical, obviously, there are regulatory issues, but even non-medical aesthetic laser applications, which to a large extent are not regulated, still can cause harm. We recently saw a customer of ours showed us photos of a pretty badly burned patient who was harmed by a customer of theirs not setting the correct settings in their IPL system. Nobody wants to go there. Okay. Where do the specified accuracy values come from? So let's just quickly get a very, very general idea of a generic calibration procedure. We start with a perfectly stable laser, or as close to perfectly stable as we can manage. We have what we call a master sensor. We periodically send representative sensors from various product families of ours to NIST for them to calibrate. Costs a bomb, takes a long time. We get them back. We call that our gold master. Against the gold master, we calibrate silver masters, second generation. The gold masters then get locked away in a cabinet. And in our production, in our laser labs, we use on a day-to-day basis the silver masters. We periodically take the gold masters out of those cabinets and compare them to the silver masters, just to make sure that the silver masters haven't drifted for some reason over the course of that time. We put the master in front of the stable laser and we take a measurement. We then quickly replace it by the sensor under test and we measure again. Even though we do it quickly might mean it takes a half a second to do that switch. If the laser power actually changed during that half a second, then we're going to be calibrating the unit under test to read the same as the master, but the power is no longer the same as it was. So that would be a bad calibration. So we want the laser to be as stable as possible. Then we measure with the unit under test, the sensor under test, sensor being calibrated, and then we adjust it, as we said before, strictly speaking. Okay, now we can forget about that bit. We adjust it so that it reads as close as possible to the master, and it has now been calibrated. And the sensors that finish production or that get sent by customers to us for their annual recalibration get calibrated against these silver masters. If it's a thermal sensor being used for single shot energy measurement, there's an additional step. We have to create that pulse whose energy we're going to measure. Instead of using a pulse laser, it's actually more accurate to use a very stable CW laser and then use an electronically controlled shutter, timed shutter, to create the pulse. We have better control over the pulse this way. The overall accuracy, the overall uncertainty in this whole calibration process depends on a bunch of different factors. Just how stable that laser really is, uniformity over the surface of the master and over the sensor being calibrated, and that could interact with the beam size and the beam position to introduce another variability in the calibration, so we need to control that. The transfer accuracy from the gold to the silver to the sensor being calibrated, to a certain extent we do have automation in the process, but at the end of the day, there's human beings, very highly skilled technicians, but still human beings that are performing, overall this calibration process, and there is a certain uncertainty that's still there. Linearity with power, we calibrated 100 watts. How sure are we that that calibration still holds at 150 watts? We have to quantify all these things, which we do. Wavelength, we have some sensors whose absorber has a very flat spectral response, and it might be enough to calibrate at one wavelength here, one wavelength there, and then over the whole spectral range, we are confident that the accuracy will be within the numbers that we specify. We have other sensors, though, whose spectral response is very not flat, and here it won't be enough to calibrate at 2 or 3 or 5 points. We have to calibrate using a full spectral curve with a computer-controlled monochromator, and then we need to anchor that whole curve at a certain number of very specifically chosen laser wavelengths, and so on. Remember this slide? We're going to come back to it in a couple of minutes. For pulse lasers, pyroelectric sensors used for pulse energy measurements, there's frequency effects that also have to be quantified. If you look at the bottom of pretty much every single sensor model's web page on our website, the bottom section of the web page is called resources and technical notes, data sheets. Right near the bottom of the bottom, there's going to be a section called technical articles. The first article in that section, just search for it. It's called Ophir Power Energy Meter Calibration Procedure and Traceability Error Analysis. It's a very clunky name, I know, but it happens to be descriptive. If you just remember error analysis, and you just on the search bar, the search window at the top of every page of our website, you search for error analysis, I think that'll bring you straight to this particular article. It was written by our founding and recently retired CTO, Dr. Ephraim Greenfield. And basically this goes through the entire calculation for every different type of sensor. I'm just going to show you one snippet as an example. For thermal power sensors for powers up to 1 kilowatt. For average power measurement. So we start off with the uncertainty of NIST calibration, which is a number that NIST publishes. In this case, it happens to be plus minus 0.5%. At the higher powers, it can be as much as 1.5%. The transfer of calibration from the NIST gold master to the silver master from statistical data that we've collected over the 40 plus years that we've been doing this, we've found that to be the number that represents that, et cetera, et cetera. Additional error from variation in absorption over the wavelength region. And then the statistical combination of all of those, the final total power calibration error, plus minus, in this case, 2.4%. In our data sheets, in this case, we're not going to write plus minus 2.4%. We're going to write plus minus 3%. at least at Ophir, an important underlying principle is that we always prefer to understate, so that when you get a piece of equipment with its specifications, you can rely on those specifications in your sleep, in whatever it is. We want you to know exactly what this instrument will and will not be able to do for you, plus a little bit of a safety margin. It's a principle that's very important to us. And so on for other types of sensors, energy sensors, high power, lower power, photodiodes for very low power sensors, and so on. So as I said, I gave you just a taste, but I'm pointing you in the direction of where much, much more detailed information is available. We want that information to be available to anybody who needs it. Okay, moving along. Maximizing measurement accuracy of some passing interest. All right, so let's begin with what we as a manufacturer of this instrumentation have done and continue to do, and then we'll talk about some best practices that you can do. So it's important to be aware that we're constantly trying to advance, and we're always making improvements. To a very large extent, the improvements are small and incremental. We shave off another 0.5% here. We figure out a way to, to improve another 0.3%, but these things add up. So over the years, we've made some pretty significant improvements in our thermopile discs. We've developed our own in-house process so that we have full control over the technology that we use to manufacture these discs. It's obviously very central to everything that we do. Better constantly improving the linearity with power, the uniformity across the surface of the aperture, so that we're constantly making those little shaves and trims to keep making the accuracy a little better and a little better and a little better. Usually that's the way to go. Sometimes there's a big step forward, but that's rare. Over the years, we've developed an improved process for maximizing the accuracy of the energy per pulse sensors, the pyroelectric sensors, so that the calibration is as independent as possible of pulse-to-pulse instability. I could tell you how we do that, but then I'd have to kill you, so I think we'll skip that bit. Any of you who recognize where that line comes from, you're obviously over a certain age, as I am. Okay, as I mentioned earlier, over the years, we've introduced, wherever possible, automation so that the transfer accuracy can be as tight as possible. At the end of the day, there's absolutely no substitute for the incredibly highly experienced and highly knowledgeable technicians and engineers and physicists who are involved in these processes. But where possible, we have introduced automation. And over the last couple of years, here's an actual number, the automation that we've been able to introduce has trimmed the transfer accuracy from plus minus 0.5% down to plus minus 0.1, 0.2%. That's a pretty significant improvement. We've got a very extensive range of lasers so that we, as rarely as possible, will have an application that falls in between the cracks. We want to use lasers, we want to calibrate at as many different sets of conditions as possible. And we've been doing this for over 40 years, as I said, and we try to verify these tests again and again under as wide a range of test conditions and laser conditions as possible. And I mentioned earlier the ISO 17025 certification. I should just say a couple words about ISO 17025. In theory, it doesn't really apply to us. Now, why is that? Because in theory, it's a standard that defines the quality of work procedures and processes for a laboratory that offers calibration as a service, meaning a third-party service. We don't do that at Ophir. At Ophir, we don't offer calibration services third party. We don't calibrate anybody else's anything. We calibrate the instruments that we manufacture as one of the last steps in the manufacturing of these instruments. We don't offer calibration service. We offer measurement solutions. So in theory, we shouldn't need to get certified to ISO 17025, but that's in theory. In practice, the world has come to look at, or the industry sees ISO 17025 certification as a measure of how good you are at calibrating, at the quality of the calibration performed by the lab, even if it's not offered as a third-party service. So over the years, we, of course, got ourselves certified instead of arguing philosophy, you know, with ourselves. Okay, maximizing measurement accuracy, some best practices that you, the user, can adopt, should adopt. Probably the most obvious and most major, and maybe the most overlooked one, is keep to your recalibration schedule. All precision measurement instruments drift with time and use. And I keep emphasizing that because even if there was no use, even if you never took the thing out of the box in which it arrived and it sat on a shelf, after a year, you will find that it has drifted a little bit. We recommend to recalibrate the instruments you get from Ophir once a year when it's newly purchased. So the first recalibration we recommend after a year and a half, but from there on, once a year. There's a sticker, a label on every instrument. For the sensors, it's usually not on the body of the sensor. It's usually this little plastic flag that's attached to the cable coming out of the sensor. And again, it may be a regulatory requirement, it may merely be a market requirement, and it may merely be a good idea. But it'll almost certainly be one of those. And I underlined the word recommend because we're not calibration police. If you're in the medical industry, then the FDA or the body that issues the European CE for you might be, in a sense, a calibration police. But otherwise, it's a recommendation, again, as we discussed earlier. Some other things you can do. I should mention that the annual recalibration applies to the meter, the display, as well as to the sensor. The meter is also a precision measurement instrument. It's not just a display. Years ago, we used to call it a display, but we changed and we started calling it a meter because in essence, what it really is a very smart picometer with a lot of functionality added, but it is a precision measurement instrument. True, its contribution to the final overall uncertainty is only about plus minus 0.25%, plus minus 0.5% when it's more than a year old, which is much less than the contribution to inaccuracy of the sensor, which is typically plus minus 3%, but still, if it's not periodically recalibrated, this can certainly increase and become a potential issue. You want to keep your sensor clean. What you're looking at here is a thermal sensor that at some point must have had some kind of organic contaminant splashed onto it. Had the user then cleaned it off with you're following the recommendations that every manufacturer will give for the particular sensor in question, in this case, a simple soft tissue that's standard in every optics lab, and a simple solvent like acetone or ethanol or something like that would have been cleaned off very easily. But in this case, it wasn't cleaned off, and the next exposure to a laser beam burned it on. There's no way to get that stuff off now. This sensor is going to need a relatively expensive disc replacement. Prevention is always better than repair. For thermal sensors, maintain a stable thermal environment during the measurement. Thermal sensors can typically respond to a change of temperature of just 1 degree Celsius per minute, and that could affect the measurement. They're that sensitive. Photodiode and pyroelectric sensors have some kind of a temperature dependence. Usually it's very small. In the case of Ophir pyro sensors, there's compensation for that built into the sensor. So those issues are probably pretty negligible in the context of this stability. But for energy measurements using pyro sensors, what's more important is that you minimize acoustic noise. Pyroelectric sensors will respond to acoustic pulses with the same physical mechanism by which they respond to laser pulses. So if there's noisy machinery in your building, the vibrations coming up through the floor much more readily than through the air solid. If it is a potential problem, you'll possibly notice jumpy readings, false triggering. So you could do something as simple as add some damping between the mounting base of the sensor and the optical table to damp out those vibrations. Ophir pyroelectric sensors also have a user adjustable threshold, so you can hopefully find that Goldilocks level that'll keep the noise out but let your laser pulses in. So that's a nice feature to have there. As far as possible, to the extent that you can control this, keep your beam centered on the sensor's aperture and of constant size. When we calibrate our sensors, we keep the beam centered, and we generally set things up so that the beam fills 1/3 to 1/2 of the aperture. So if you, when you're doing your measurements, keep your beam centered and of constant size, more or less around the same order of magnitude, you're removing a variable, and therefore you're eliminating or at least minimizing another potential source of uncertainty. In general, and this is good advice for any kind of measurement, you want to keep away from the bottom of any given scale, possibly also from the top of any given scale, although that's actually less important. By keeping away from the bottom of any given scale, you're keeping your signal to noise ratio okay, and you're avoiding some other issues. If you need better absolute accuracy than what's specified, special calibration might be possible in some cases. Check with us. Now, what do I mean by special calibration? So you remember this from a couple slides ago. It's one of the things that I said to remember, that the overall accuracy of our calibration process depends on the laser stability, uniformity over the surface, etc., power linearity, wavelength, frequency effect, all of those different things. So we normally calibrate with the beam centered and filling about 1/3 to 1/2 of the aperture, as I said. So most of these are eliminated from the calibration process, but the user's application might not sit at exactly these conditions of wavelength, power, pulse frequency, or whatever. So if we can instead tighten some of these and calibrate at the customer's exact wavelength, which might not be the standard wavelength or one of the standard wavelengths at which this sensor model normally gets calibrated, wavelength, power, pulse rate, any of the parameters. We can even tighten the final inspection tolerance so that the sensors that come out will have a smaller variation. Then we could, in principle, ensure that the calibration will be at parameters as close as possible to those of the user, and therefore tighten the final deliverable accuracy in the measurements that you're going to get. I keep on saying in some cases, sometimes we can, sometimes we just can't. If it's a wavelength that's exotic and we just don't have a laser at that wavelength, unusual, but it has happened, that'll be one example. I'll mention that pyroelectric sensors that we use for pulse energy measurement are already pretty much at the maximum accuracy that they can be brought to. We've done a lot of fancy stuff there. There's not much room to shave off a whole lot more, as an example. So again, in some cases we can shave off even more. In some cases we can't. When we can, then there will obviously be some extra level of cost involved, depending on what degree of extra work is needed, special setups and that sort of thing. But in some cases, it is doable. And for the last couple minutes, I just want to, as I mentioned, do a quick breakdown of what's in the certificate of calibration. So here's an overview of the Ophir C.O.C, and I've divided it into sections, and I just want to tell you in a few bullets what each section means, what's there. So let's begin with A, that's the ISO 17025 accreditation logo. That's standard in almost all of Ophir's catalog sensors. The scope of our ISO 17025 certification is available on our website. You can look for it under, I think, support or resources. I don't remember which. You look for ISO certification, you'll find the certificates and also the scope. Certain power ranges, certain whatever it is, are outside the scope. Very few, but there are some. And so in this case, it's the Israel Laboratory Accreditation Authority in our calibration facility in Germany, in the US, and in Japan, it'll be the relevant logo of the standards body that certified each particular facility. B, okay, those are the parameters to identify the device being calibrated, the serial number of the sensor, the model number and its name, the description, and also the certificate number if this is the third certificate being issued for that serial number that'll show up that'll be stated there as well. C, okay, measurement uncertainty. We mentioned this earlier. Now we're going to explain it. Here, measurement uncertainty 1.9%. The measurement in this case refers to the calibration process that we performed. I.e. the process of comparing the reading of the sensor being calibrated with the reading of a calibration master. Now, in the ideal case, the calibration master is perfectly errorless, noiseless, and it's absolutely correct. You sense where I'm going. In which case, the measurement uncertainty would not be 1.9%, it would be 0. If the measurement uncertainty really were in fact 0, and then the calibration result, the deviation that we measured in the calibration process between the sensor being calibrated and the master were, let's say, 1.5% low, then we would know with 100% certainty that the sensor being calibrated is exactly 1.5% below NIST in that particular measurement. In the universe we live in, that can never happen. There are uncertainties even in the NIST calibration itself. There's transfer error from the NIST reference to the working reference, setup instabilities, and so on. So the sensor being calibrated might be off from the truth by more or by less than the deviation that we actually measured when we calibrated it. So the answer to the question, how far off of the absolute truth is this sensor? The answer is not a single clean number, but it's a probability distribution about some number, as we said a bunch of times earlier. Calibration uncertainty is important. The measurement uncertainty, as we call it here in the document, is important for deriving pass-fail criteria to determine whether a device meets its accuracy specifications. And if you want to know where does this measurement uncertainty value that we write here come from, then for that, I refer you back to that white paper on our website, which goes through all the numbers and all the calculations. Oh, just one thing I forgot to mention. Obviously, that measurement uncertainty is the best possible specification that we could give for the measurement accuracy that you could get with an instrument. In practice, the measurement accuracy will always be a worse number than this because there are additional things involved. D, reference standards used. The serial number of the master sensors and master instruments that were used in the calibration process. We have a traceability chart on our website so that it can always be traced back to NIST or some equivalent national standards laboratory. E, the results table. Okay, here is where we have all the relevant measurement parameters and the results. In all the C.O.Cs, there will be a results column with the raw data reading of the reference sensor and its settings, what scale, what power scale it was on, what wavelength it was set to, and for the sensor under test, what scale it was set to. It might not be the same model sensor as the reference, so the scales might be different, the wavelength reading and so on. And then the deviation, the tolerance, which means the maximum allowed deviation, and then pass-fail. As we said earlier, the pass-fail is based on a decision criterion that's not just a simple number. We're dealing with statistics. And the deviation obviously is the gap between the sensor being calibrated and the master. Oh, I ran ahead of myself, but I think I already explained what these things are. Okay, F, information about the specific calibration. Reference to the internal procedure number that we used, again, so that everything is traceable, who performed it, the date, the environmental conditions, the temperature in the lab, the humidity in the lab, and so on. G, reference to the website where all the data sheets can be found. And H, this is the bit with a whole lot of text that probably only the QA professionals would be interested in reading. This is information relating to the calibration, the accreditation, particularly the decision rule that's used to determine pass-fail, and so on. Okay, and just to round everything off regarding the terminology, when we use the word calibration, as I said earlier, we use it loosely to refer to measuring the deviation between the sensor being calibrated and the reference, and then adjusting it so that it reads as close to the reference as possible. ISO professionals don't mean that. And it's important that we understand each other. The quality assurance professionals, when they use the word calibration, they mean specifically measuring the deviation and stopping there, adjusting the instrument so that it then reads the same as the reference. They have a different word for that. They call it adjustment. So it's just important to know how to translate from QA language to engineering language. Okay, so in summary, we talked about the meaning and importance of accurate calibration and when is it important and when maybe might it not be so important. I pointed you in the general direction of detailed information about where the accuracy specification values that we use come from. And I think there's a lot of importance in the fact that we have that information available for you. We talked about some things in general that Ophir does, and presumably other manufacturers do similar stuff to maximize the calibration, the accuracy that you can achieve with a given instrument. And we talked about some black belt best practices that we recommend, that we highly recommend that you adopt if you haven't already, to further maximize the accuracy that you can achieve with any given instrument. And then we had a look at the Ophir certificate of calibration and the information that's in it. That's what I wanted to cover today. Let me just see if there were any questions that I missed. No, there weren't. Okay, good. So if you have any questions you want to ask online, you have a few more seconds in which to do so. Otherwise, you're more than welcome to contact me offline. My name again is Mark Slutsky. Here's my email address. I'm going to leave this up for a minute or so after we're done in case you want to take it down and get a hold of me. You can also get a hold of me, us, through our website, through the Ophir offices, or our partners in your various countries. I hope this was helpful and, dare I say, maybe even interesting. Thank you very much for joining us today. Have a really nice rest of the day.